Welcome back to our next lesson on quadratics, and specifically we're looking at a special kind of quadratics today, the perfect square. So by now you should be very familiar with factoring using the decomposition method, so let's try. Here we have A is 9, B 12, and C is 4. And we want to find R and S so that their sum is 12 and their product is 36. And trying the method that we saw from last class, we should be able to find that R is actually equal to S, and it'll be 6 because 6 plus 6 is 12, and 6 times 6 is 36. So, using the decomposition method now, I will rewrite this as the 12x as 2 6x. So 6x plus 6x. And now I'll try to factor the common factor between two terms. Okay, so you should receive that. And we see that they both have that 3x plus 2. But wait, if you look here now, we have 3x plus 2. 3x plus 2. So this is actually 3x plus 2 squared. Now let's take a look at our algebraic tiles, which is a representation of this expression. So we can see that we have 3x here and a positive 2. And same with this side, we have 3x and positive 2. And so this algebraic tile is actually a perfect square. Now, let's look at another example of 9x squared plus 6x plus 4. And I want you to try to think, why is this one not a perfect square? Specifically, if we are looking at the square here, if we had 9x, we would have all of these squares here. And if we also had 4, we would have these 4 squares. Oh, that's not a square. We would have these 4 squares here. Now, in order to complete the bigger square, here I need to have 2, and here we need to have 2, so that our x tiles are 12. But if we only have 6 x tiles, I will not be able to have this row and this column, perhaps. Or one, or maybe 2 of the columns or 2 of the rows. And essentially, you will see that you will not be able to, from those tiles alone, be able to form a perfect square. So that expression is not a perfect square. Now, is it factorable? So we're going to test. Do we have R plus S equals 6 and R times S equal 36? I'll give you a moment to think about that. So if you try trial and error or the method from last class, you'll be able to see that there are no two integers R and S that fit this description. So it is actually also not factorable. So now, how can you recognize a trinomial, so an expression with 3 terms, that might be a perfect square? So to do that, we're going to look at the definition of the perfect square. So a perfect square is our polynomial of this form, and specifically pay attention to these terms. So this will be a perfect square trinomial, and it will be factored as ax plus or minus b squared. So let's look at expanding these two first. So if I have ax plus b squared, I will use the FOIL method, which I also shared a video for that with you, so you can take a look at that. you'll be able to get this. So essentially, if you are multiplying the inside terms, you get a squared. And if you multiply the outer terms, you get b squared. And if you multiply the inner ones or the outer ones, you get ab, but twice. So that is why we have that a squared x squared and the b squared at the end. And in the middle, it's 2ab because we have two of those terms from the inside terms and the outside terms. Similarly, we'll see the same for when we have a negative, where our first two terms are going to give us a squared x squared. Our outer term now, it's negative b times negative b. So it's still going to be plus b squared. But now our inside terms and the outside terms are going to look different because it's ax times negative b. So it's actually negative ab twice. And so this will be a squared x squared minus 2ab plus b squared. So now going back to our question of how can you recognize a trinomial that might be a perfect square? Essentially, we want to see, do we have that a squared and the b squared? So is the coefficient of our x squared a perfect square? And is our constant term also a perfect square? And if so, we'll also check if that middle term is double the square root of the coefficient and the constant term. So let's take a look in an example. So consider 16x squared plus 24x plus 9. So first we're going to check if the coefficient of x squared is a square. And you should recognize that 4 squared is 16. So yes, it is. Next, we check if the constant term c, which in this case is 9, is a perfect square. And again, 3 squared equals 9. So it is. Now, we're going to check if that middle term is 2ab. But a is not 16, it's 4. And b is not 9, it is 3. So 2ab will be 24, because 2 times 4 times 3. And so we do actually have that 24 there as well. And that's what I've done over here. So now, based on our definition of a perfect square, we know that we can write as ax plus or minus b and then square that. So here we will have 4x squared plus, 3. This should not be here. So 4x squared, 4x plus 3, and the whole thing squared. And again, you can try now expanding this. So maybe I'll just show you this one as an example. 4x plus 3, 4x plus 3. We will get 16x squared. Our middle two terms are going to give us 12x plus 12x, and finally a 9. And so we have 16x squared plus 24x plus 9, which is our original expression. So now let's try this again, but with decomposition method. So we know that 16 times 9 is 144. And we also know that 12 times 12 is 144. And 12 plus 12 is also 24 here. So now we will decompose this to 12x and 12x. And if we factor from here, we will have a 4x and a 3 here. And again, if we factor out that 4x plus 3, which is common, we get 4x plus 3. Or in other words, 4x plus 3 squared. And now you should recognize that our first example, that's exactly what we did. We found 6, where 2 times 6 was 12, and 6 squared was 36. So either way will give us the same answer, but now we have a faster way. So if you recognize a quadratic function to be a perfect square based on its definition, you have a very simple way of writing it in factored form. Now let's look at one more example where we have two variables. And don't let this fool you. It's still the same idea. So the first term here, 4n squared, we're checking if it's a perfect square. And 2 squared is 4. And n squared is n squared. So essentially, 4n squared is 2n. Now let's look at the last term here. 49, or 7 squared, is 49. And also, m squared is m squared. Now, if we square root 49 m squared, we get 7m. So we know that our first term, if we multiply it, here we get 4n squared, and that's correct. And our last term, we get 49m squared. That's also correct. Now, I have two positives here. So when I multiply, when I multiply the inside and the outside terms, I also want to be getting 14nm. And pay attention here that there's two variables, so you have to include both n and m. And I'll move this a little over, but we also get a second 14nm term if you are expanding with addition. And if we now collect this, it will be the original expression we started with. So the factored form was 2n plus 7m squared. So don't let that second variable in there fool you. It's still the same idea. We still have that square root of a, which is 2, the square root of the constant term, which the constant term here has an additional variable with it, m. And so we get the 7m. And I just showed you the check that 2n plus 7m will give us that same expression. Today, we're also going to look at one more type of quadratic function, and that is our difference of squares. So these types of quadratics are actually binomials. They only have two terms, such as here 4x squared minus 9. If we use algebraic tiles to represent this, I have my 4x squared squares, and I had 9 of the -1 tiles as well. And each of these form two perfect squares. And I want to see if I can combine this somehow or form a shape where I can complete this bigger square here. So our square is not complete, so we're trying to complete it. So that's what I've done here. So here I have side lengths x and x. And here I had -1 and 1. So these tiles here have become 6 of the negative x tiles, and we have 6 of the positive ones. But why did we add 6 of the positive x tiles and 6 of the negative x tiles? What do you think? So by doing so, we've created a complete square without changing our original expression, because 6x and -6x is equal to 0. So technically we didn't add anything, although in our visual diagram it looks like we have added 12 additional rectangles. The positive x and the negative x actually cancel each other out. So again, we haven't added anything. This is the same as this shape. So now, 4x squared minus 9 is a square made up of side lengths. If we look here, we have 2x minus 3 over here. This is 2x minus 3. And on this side, we have 2x positive 3. And the positive and negative come from that adding and subtracting the 6. So 2x plus 3 and 2x minus 3. And so the area, which was 4x squared minus 9, our expression to begin with, can be written as 2x plus 3, 2x minus 3, which is the product of the side lengths of the square. So we're going to try now decomposition method with an additional step. We will see this later on as well, where we add the zero identity, where we use the zero identity property to add values in that are essentially zero values, such as adding plus 6x minus 6x, which is 0. So here, I first look at A and C. So we know that 4 times negative 9 is 36, but here B is 0. But how would that work? And the key thing here is that 36 is a perfect square. So 36 is actually plus or minus negative 6 as its square root. So we see that positive 6 times positive 6 gives us the 36. Oh, sorry, negative 36. And also that 6 and negative 6 is equal to 0, which is that same b that we wanted. So this is essentially the same as plus 6x minus 6x. And now, if I factor out the 2x from here, we would get 2x plus 3. And if I factor out the negative 3 from here, I'll get also 2x plus 3. And they both have that 2x plus 3 in common. And so here we have 2x minus 3 times 2x plus 3, which is what we were expecting. This is our second special kind of quadratic, and this is a polynomial of the form a squared x squared minus b squared, and it's called a difference of squares. And I hope you can see why it's called that, because the first term, a squared x squared, is a perfect square, and b squared is also a perfect square. So these two are a difference of two squares, and so it's a difference of squares trinomial. And when we factor them, we need to know what the square roots were, so essentially a and b, and we can write it as ax minus b and ax plus b. So in our example above, because we knew that the square root of 4 is 2 and the square root of 9 is 3, we could have right away wrote 4x squared minus 9 as 2x plus 3, 2x minus 3, without doing any of this additional work that we just did above here. So just based on knowing the definition, you can make this assumption and acknowledge that it is a difference of squares, so you are able to apply this. So that is the end of our lesson for today. So I'll go over the practice set with you. So here, I want you to try to identify the polynomial, which is the area, and its factors using the side length. So again, we're practicing those algebraic tiles. Now, on the second page, we have a lot of factoring with perfect squares and difference of squares. So get familiar identifying these two forms. They're very special. And once you start recognizing a few of them, you get the hang of the perfect squares that we're looking for as well. Those values like 136, 144, 121. So get familiar with these as well. And some extensions as well. So anytime you see that light bulb, it is a bit of an extension problem. So again, I highly encourage you to try it. But if you're struggling, send me an email, leave a question on our Google Classroom lesson, and try your best. And I hope you learned a lot more about quadratics today. And next class, we're looking at our last way to factor and wrapping up shortly factoring quadratics altogether.